Welcome to the first part of the solutions to the lecture problems for Chapter 7. Let's begin with the first problem. Here, we're told that a weightlifter lifts a barbell that weighs 700 newtons at constant velocity over a displacement of 0.5 meters. We're asked to determine the work done on the barbell by the weightlifter and by the force. We have a little video animation, but before we play it, let's go ahead and draw a free body diagram of this situation. The x-axis, y-axis. Let's place the barbell at the origin and look at the forces acting on it. Well, one force is the force of gravity, which is equal to the weight of the barbell. The other force, which is the lifting force, has to equal the force of gravity in magnitude because we are told that the lift occurs at constant velocity, which implies that there is no acceleration along the vertical. This, by the way, is the displacement which is given to us, delta R, and because this is the lifting phase, we know that delta R will be equal to 0.5 meters in the positive j hat direction. In other words, the lift is upward. Okay, now, having established that because a sub y is equal to 0, the net force in the y direction then must equal 0, so that F sub L minus mg, or in other words, F sub g, equals 0, implying that F sub L has a magnitude equal to mg. And if we write this as a vector with the given direction for F sub L, we see that mg in the positive j hat direction is the value of F sub L. On the other hand, F sub g, the force of gravity, also has a magnitude of mg, but because it is directed downwards, see now that we are giving the directions in terms of the unit vectors, we see the sign of the values of these forces. And so to determine the work done by F sub L, we use the definition of work, F dotted with delta R. F in this case is F sub L. Delta R in this case, delta R is 0.5 meters in the positive j hat direction. We make a substitution that F sub L equals mg in the j hat direction, positive. We dot that with 0.5 meters in the j hat direction, and this gives us positive mg times 0.5 meters, and positive mg, we're told, is 700 newtons, and so the work done by the lifting force is 350 joules. On the other hand, the work done by the force of gravity, F sub g, dotted with delta R, F sub g is equal to minus mg j hat, dotted with 0.5 meters, positive j hat, because it's upward. We see that we get minus mg times 0.5 meters, or in other words, the work done is equal to minus 350 joules. Notice that the net amount of work done on the barbell is equal to 0. Each of the forces does the same magnitude of work, but in the opposite direction. And by the work kinetic energy theorem, this implies that there should be no change in the kinetic energy of the barbell, which means that V is constant both in speed and direction. So the speed portion and the direction portion. In other words, this barbell is being lifted upward at constant speed. Okay, let's go ahead and view the animation that corresponds to this problem. It's called lifting a weight. Let's see if we can make this work.
A weightlifter lifts a barbell against the force of gravity. If we assume she lifts it at a constant velocity, she must exert a force just large enough to balance the object's weight, mg, while displacing it through a distance, h. Because the force and displacement are in the same direction, the work done on the barbell by the weightlifter is positive mgh. Meanwhile, gravity exerts a downward force mg on the barbell, so the work done on the barbell by gravity is negative mgh. The net work done on the barbell, the sum of the work done by the weightlifter and by gravity, is zero. Although the woman exerts tremendous physical effort when she holds the barbell at constant height, she performs no more work in a physics sense because there is no further displacement.
So, in other words, for work to be done, there has to be a force applied to an object as it is being displaced. Okay, next problem. A man pulls a vacuum cleaner of 24.6 kilograms with a force of 50 newtons at an angle of 30 degrees with the floor. The coefficient of kinetic friction, mu k, is equal to 0.2. Calculate the work done on the vacuum cleaner by the forces that are shown as it is being displaced 3 meters to the right. Well, hopefully you have your notes at hand and you can see the diagram that is provided, which for some reason on my notebook page does not appear. So let's see if we can't reproduce this diagram as best as I can with this pencil. First, let's agree that delta R is equal to 3 meters. Now we want to draw a free body diagram because to determine the amount of work on the vacuum cleaner, we sort of need to know the value of the forces that are acting on it. So let's draw an XY coordinate system, or in other words, a free body diagram. Place the vacuum cleaner at the center, and we see that the force that the man exerts has components since it acts 30 degrees to the horizontal. So we have an F sub x, and we have an F sub y, and this will become important for us when we determine the work. We can calculate F sub x, 43.3 newtons, F sub y, 25 newtons. We know that the vacuum cleaner has weight. All objects on the earth have weight. And mg here is equal to, let's see, 24.6 times 9.8 is 241 newtons. Okay. And let's see, there is friction that prevents the motion of the vacuum cleaner, and I don't know why the arrow points to the right, because friction is actually pointing to the left to oppose the motion. And of course, friction has to be determined. All we know is that it equals mu k times n. And because the vacuum is on the floor, we know that there is a normal force supporting it. So now we can begin systematically to calculate the work done on this vacuum cleaner. Let's start with the work done by the normal force. Okay, so what is the normal force? Well, we know that there is no displacement or acceleration along the y direction. So n minus mg plus f sub y equals 0, And when we solve for n and we plug in all the numbers, we find that n is equal to 216 newtons. And if we write this as a vector, it's in the positive j hat direction. So the work done by the normal force N dot delta R equals 0. Why? Because delta R is in the I hat direction, N is in the j hat direction, and if you recall, j hat dot I hat equals 0. So no work is being done by the normal force. What about the work that is being done by the force of gravity? Okay, the work done by F sub g. F sub g dotted with delta R. What is F sub g? F sub g is, of course, mg in the negative j hat direction. Here again, we see that the work done by F sub g is 0 because minus j hat dotted with I hat is equal to 0. Okay, what about the work that is being done by the force that the man exerts on the vacuum, which we merely label F? Well, here, if we consider that F has two components, one which is in the I hat direction, okay, that's F sub x. The other is in the j hat direction, okay, F sub y. Coming over here, you can see that the only component that contributes to the work is F sub x. And so here we have F sub x, I hat, dotted with, okay, let's go ahead and write F sub y j hat, but you know that this term is not going to contribute anything. Dotted with delta R, which is 3 meters, I hat. You can see that j hat dotted with I hat will be equal to 0 for the same reason that we wrote here, j hat dot I hat equals 0. And so the work done by F will be merely F sub x times 3 meters, okay, 3.00 meters, and that work works out to be plus 130 joules. What about the work that is being done by F sub k? Well, the work done by F sub k, let's write F sub k dotted with delta R, is mu k n in the minus I hat direction, dotted with 3 meters in the positive I hat direction. Well, it's a good thing that we determined what the value of n was, because that allows us to determine what the value of F sub k is. Well, once we substitute the fact that we have n is equal to 216 newtons, and mu k is given as 0.2, we get here F sub k is equal to minus 43.2 newtons in the I hat minus I hat direction, dotted with 3 meters in the positive I hat direction, and lo and behold, we get minus 130 joules worth of work. Now, there are no other forces because F had two components. We only took into account the component that contributes to work. So when we sum all of the work, we find it equals 0, which once again implies this vacuum cleaner must be moving at constant velocity. In other words, there is no acceleration in the x direction, and of course none in the y, since the vacuum cleaner is on the ground. Next question. Here, this is a mathematical question. We don't have vacuum cleaners or barbells. We're just merely given a force 6I hat minus 2j hat acting on a particle as the particle undergoes a displacement delta r of 3I hat plus j hat. The question is, how do we determine the work? Do we use F dot delta r, or do we use the integral of F dot dr? What is appropriate here? Well, look at the form of the force. Does it have an xy dependence? In other words, is the force F a function of x and or y? The answer is no. And the way we know this is, look, we have 6I hat minus 2j hat. These are constant, okay? So that means we do not have to use the integral form to solve for work. We can merely take the dot product of 6I hat minus 2j hat with 3I hat plus j hat. Now this is in newtons, this is in meters, so let's keep our units. And 6I hat dot 3I hat gives us 18. 6I hat dot j hat gives us 0. Minus 2j hat dot 3I hat is 0. Minus 2j hat dot j hat is minus 2. So the work done by this force is 16 joules. Okay, 16 joules. Notice that it's a scalar. Work itself is never a vector. It is a scalar. It can either be positive or it can be negative, but it will never have a unit vector associated with it. No I hat, no j hat, no k hat. Okay, next problem, and last problem for this part of the solution for chapter 7. Here, a force 4xi plus 3yj. Look at the form of F. Is this a force that has an xy dependence? The answer is yes. There are x's and y's, so this is a force that depends on position. This force is variable with position. And it acts on an object as the object is displaced from x equals 0 to x equals, let's see, our number got cut off, and the answer is 5 meters, I believe. I believe it's 5 meters. What is the work done by the force? Well, here, the work has to be determined by taking the integral of F dot dr. Okay, so how do we write dr? Well, dr has two components. It has a dx component, I hat, plus a dy component, j hat. The question is, which of these is appropriate in this case? Well, our variation is only in x, so dy is 0, there is no variation. So dr is merely given as dx I hat. So let's substitute. We have 4x I hat plus 3y j hat dotted with dx I hat. And the variation in x is x goes from 0 to 5. Well, let's do this dot product. 4x I hat dot dx I hat is 4x dx, again 0 to 5. 3y j hat dot dx I hat is 0. And so our integral is merely 4x dx, which is 4x squared over 2 from 0 to 5. 2 of the 4 gets canceled by the 2 here. So 2 times 25 is the work done, which is equal to 50 joules. And again, this is positive 50 joules. Notice there's no I hat or j hat. So very important to keep in mind when you use integration and when you use merely the scalar product with no integral. Well, this concludes the second part of the problem-solving session for Chapter 7. Until next time.